So, the dipole moments of compounds, dipole moment is directly proportional to difference in electronegativity. Similarly, in ionic substances, which we call as very highly polar covalent compounds, how to compare ionic nature? Look here. F minus O2 minus N3 minus C4 minus. Among these ions, the sizes, the radius among isoelectronic species F minus, O2 minus, N3 minus, C4 minus. These are all isoelectronic. Isoelectronic in the sense they have equal number of electrons, 10, 10, 10, 10. Among isoelectronic species, more is the negative charge, more negative, more size. More negative, more size. So, the radius of F minus smaller than O2 minus, because greater the negative charge, biggest is the size. And of course, opposites are opposite. I need not say more positive, less size. More positive, less size. So, among isoelectronic species, more negative, more size. This is one principle that helps you in finding ionic radii. And second principle in continuation to that is small cation more covalent. Small cation more covalent. What does that mean? Suppose a compound in which the cation is small, for example, you have LiCl, NaCl, KCl, NaCl, KCl or BCl. So, which is more ionic or which is more covalent? So, ionic nature, what happens? Small cation. Among them, you know, Li plus is the smaller one, Na is bigger, K plus is still bigger, or B plus is still bigger. So, smaller the size of the cation, small cation more covalent. Therefore, ionic nature goes on increasing. RBCl is more ionic than KCl. That's why I always tell you, it's not possible to brand a particular compound as ionic or covalent. I can only say this is more ionic than that or less ionic than this. Ionic nature can be only relative, but absolute ionicness perhaps is very difficult to decide. But of course, you can say all compounds formed by elements of 1A, lithium, sodium, they are perfectly ionic. But LiCl has more covalency. What does it mean? Lithium being a small ion, LiCl minus. So, what happens is, this positive charge, since it is very small, the negative charge is once again attracted. Lithium no doubt gives electron to chlorine, but it also pulls the electron more towards itself. It is very highly polar, but not very highly polar. So, lithium gives and takes. What is that give and take nature called giving and taking? That is nothing but sharing. The sharing nature is called covalency. So, among isoelectronic species, more negative, more size, more positive, less size, more positive, less size, and small cation, more covalent. Opposites once again are opposite. How? What is the opposite of small cation? Small cation, small anion. The opposite is small anion, not large anion. Don't change these two. Either change small or either change cation. Take the opposite of this or the opposite of that. Small cation, large cation. Small anion, large anion. Now, compare the ionic nature of these fluoride, oxide, nitride, carbide. Which among them is more ionic and which among them is most covalent? Let us see. Small cation more covalent. Small anion opposite. Small anion more ionic. Small anion more ionic. Therefore, small anion, this one is more ionic, F minus is more ionic, C4 minus is more covalent. Therefore, once again, ionic nature also, fluorides are more ionic than oxides, more ionic than nitrides, more ionic than carbide. And it is common sense to understand fluorine doesn't have the tendency to share with others. It will, if necessary, it will forcibly take the electrons of others, being most electronegative. So, F minus doesn't easily part with its electron. Even if the other one, here Cl minus is still giving something back, but if it is F minus, perhaps F minus will not give to lithium plus. So, you take the fluorides of the same element. Here I have taken chlorides of different element. I have kept the anion the same, Cl minus in every case. I have changed the cation, but this time I will take LiF, LiCl, LiBr, Li. So, lithium's tendency, lithium being small, it also wants to take the electrons back, but F minus doesn't give that easily. Therefore, ionic nature here, fluorides are more ionic than chlorides because small anions more ionic, small cation more covalent, small anion more covalent, small anion more ionic. Therefore, F minus is more ionic. So, just use these two principles among isoelectronic species: more negative, more size, small cation, more covalent. Of course, this is called the Fezan's rule. The name is not necessary. The application of the principle is necessary. Name is not necessary. And they say Li plus gives and takes it back, and claiming the charge back is called polarizing power. Claiming back, that is called polarizing power, and that polarizing power is once again polarizing power is an indication of covalent nature. Now, we have almost come to the end of chemical bonding. Molecular orbital theory. Valence bond theory. Molecular orbital theory, MOT, VBT versus MOT. Without actually naming this, we have until now used this in all things we have made while drawing the structures or while finding the covalency. We have decided valence bond theory. So, only the unpaired electrons of the valence shell, according to this theory, only the unpaired electrons of the valence shell participate in bonding. And according to molecular orbital theory, all the electrons are involved in bonding. So, only the unpaired electrons of the valence shell participate in bonding, and there all electrons participate in bonding. Look here. Chlorine has 17 electrons. 16 electrons revolve around this chlorine nucleus, and 16 electrons revolve around this chlorine nucleus, and only 2 electrons are shared in common. Only these 2 electrons. This is valence bond theory. Means this chlorine atom has a power only over these 2 electrons. This chlorine doesn't have anything to do with these 16 electrons. This chlorine can have a rightfully claim these 2 electrons, but not this. So, according to valence bond theory, only that outermost unpaired electron of the outermost orbit, that particular 3p Z1 electron only participates in bonding. But according to valence bond theory, all 34 electrons participate. 17 plus 17, all 34 electrons will participate in bonding. And you will be surprised, sir, if 34 electrons are participating, is it like 17 bonds between chlorine? Is going to be 17 bonds between 2 chlorine atoms? No, it is not so. Listen, because of course there are 34 electrons. All 34 electrons are not actually binding the atoms. All 34 are not binding. Some of them, those who are bonded electrons, some of them are bonding electrons and they are helping bringing the electrons together. Like suppose two electrons have same spin. Suppose if two electrons have same spin, what will they do? They repel. Same spin, plus half, they repel. And electrons with opposite spin, they attract. So what happens here is, all electrons do not help binding. Some of the electrons bind and some of the electrons do the opposite. Some electrons try to bring the atoms together, some electrons repel and take the atoms together. And the net bonds will be depending on the number of bonding electrons and the number of anti-bonding electrons. There are 34 electrons, no doubt. All 34 electrons are not helping in bonding. Some of them are bonding, some of them are doing the opposite, anti-bonding. So, how to find out how many are bonding or how many are anti-bonding? The bonding molecular orbital. Okay, what is an atomic orbital? What is the difference between atomic orbital and a molecular orbital? The path taken by electrons or the region occupied, the place, the region, the space occupied, the path taken by electron around one nucleus. Around one nucleus, the path taken by electron around one nucleus, atomic orbital. Here it is the path taken by electron around two nuclei. This is a molecular orbital. Atomic orbital means where the electron is present, where exactly the electron is present around one nucleus, and or where exactly the electron is present when one nucleus is acting on it, where two nuclei, it is called molecular orbital. So the electron is now attracted by two, so it is a molecular orbital. So 1s, 1p, 2s, 2p, these are called 1s, 1p, 1s, 1s, 2s, 2p, 1s, 2s, 2p, 3s, etc. They are called atomic orbitals. They are called atomic orbitals, and we have sigma 1s, sigma 2s, these are called molecular orbitals, sigma. And sigma star is called anti-bonding molecular orbital. What is an anti-bonding molecular orbital? A bonding molecular orbital is present between two nuclei. An anti-bonding molecular orbital is away from the nucleus. You can see, look here. This is a bonding molecular orbital. This is a bonding molecular orbital where two orbitals combined in a constructive manner, linear combination of atomic orbitals. This is a bonding molecular orbital where two orbitals, this is an anti-bonding molecular orbital which is away from the nuclei, away. So here these two are bringing the atoms together, here these two are taking the electrons, atoms away. So what are the bonding molecular orbitals? Sigma 1s, sigma star 1s, like that, sigma 2s. Whenever there is a star, it is called, this is a bonding molecular orbital, this is anti-bonding molecular orbital. And the anti-bonding molecular orbital configuration will be like this. Up to nitrogen means up to 14, the electrons must be filled in the following manner. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2py is equal to pi 2pz is equal to next sigma 2px, sigma 2px. So up to 14, this is how you have to arrange the electrons. That is, first two electrons here, first two, next two, next two, next two. So 8 electrons have been distributed. 8 electrons have been properly distributed, and the next 4 electrons, since these two are equal, you should give 1 to this. Then just like you remember well, among px, py, pz, the Hund's rule for atomic is px1, py1, pz1, 1 1 1, then pairing px2, py2, pz2. Similarly, the 9th electron goes here, 10th goes here, up to 8 electrons, 2 2 2 2. First 2, next 2, next 2, next 2, the 9th electron here, the 10th here, the 11th here, the 12th here. Because these two are equal, you give 1 here, then there. One pairing starts, this is Hund's rule. 9th electron here, 10th there, 11th, like this. And then of course the last 2. So this is the order, and it's sometimes very difficult to remember this order, but there is another way also. So let us try to find out the bond order of 14, I mean N2, 14. Bond order means bond order is equal to number of bonding electrons minus number of anti-bonding electrons divided by 2. After duly writing the electronic configuration, number of bonding electrons minus number of anti-bonding electrons by 2. So bond order is actually equivalent to number of bonds formed. Number of bonds formed. And of course, greater the bond order means more bonds means stronger is the molecule. More bonds, molecule is stronger. So look here, this is rule for bond order. Number of bonding electrons minus number of anti-bonding electrons by 2. And let us go back to N2. 7 plus 7, you have a total of 14 electrons. Now, sigma 1s2, sigma star 1s2, sigma 2s2. How many electrons I have distributed so far? 6. 2, 2, 2. Sigma star 2s2. 8 electrons are over. So, pi 2p y2, pi 2p z2, they are equal. But so far we have distributed pi 2p y2, pi 2p z2, 12 electrons are over, and sigma 2p x2, sigma 2p x2. So this is the order. Sigma 2px, we know that because only the 2px electron participates in bonding and the remaining 2 parts are pi bonds. In nitrogen, if you simply write N triple bond N, what is it we say? This one is sigma bond, the other 2 are pi. So the same designation is given. We say that the sigma bond is formed using px, py, pz, pi bond is formed. So pi 2 py 2 pi. So this is a sigma bond formed by 2px, this is a pi bond formed by 2py, 2py of this, 2py of that. This is a pi bond formed by this. Now, pi 2py2, pi 2pz2, sigma 2px2, this is up to 14. So, up to 14, this is the order. After 14, the order changes a little. We will discuss it a little later. But now, so how to distribute electrons? Suppose this is 14. Suppose only 4 are there. Only first one sigma 1s1. What will be the molecular configuration of one electron? H2 plus. What do you mean by H2 plus? What do you mean by H2 plus? It's only just one electron. 2 hydrogen atoms, no doubt, but I have removed one electron. So it is just one electron. Where is that electron? That is in sigma 1s1. So there is only one electron and that one is bonding. Bond order 1 by 2, 0.5. And it is common sense also to understand, you have a hydrogen atom with one electron and a H plus proton. How can they be bonded? Whether this exists or not, if it exists, H2 plus exists under certain circumstances, you take hydrogen gas and you start heating it, one of the molecules may lose one electron, but still they are somewhat bonded. Hydrogen gas, hydrogen molecule, you have 2 electrons. After heating, one electron is lost, but the remaining 2 nuclei will share that 1 electron, because they have only 1 electron, they share that. How will they share that? That single electron will be moving around 2 nuclei, that is sigma 1s1. Okay, this electron will be moving between these 2 nuclei, only 1 electron. So it is equal to half a bond, H2, H2. So what are they doing now? Look here. So hydrogen has an electron, that hydrogen has an electron. They both are using both. I have a book, my friend have a book. We both are using both the books. Suppose my book is lost, someone has stolen my book. What? And I have become H plus. What shall I do? We will be using the same book also. Earlier we were using 2 books. 2 books shared by 2 people, that is equal to 1. Here 1 book used by 2 people, 1 by 2. As simple as that. Okay. So H2 plus exists, but that may not exist at room temperature, but when heated, definitely one hydrogen molecule will lose 1 electron. Some of them may lose both the electrons. So this is the electronic configuration of molecular orbital configuration of H2 plus. H2, 2 electrons, sigma 1s2. 3, 2, 1. Means if you have 3 electrons, 2 electrons here, 1 here. 4, 2, 2. So what will be the bond order of He2? He2. So He2 means 2 helium atoms. 2 helium atoms, there are total of 4 electrons. Put 2 electrons here, 2 electrons here. So what are the 4 electrons are doing? 2 of the electrons are bonding, the remaining 2 are anti-bonding. That is, the first 2 electrons are constructing and the next 2 electrons are destroying whatever has been built. So what is the net result? 0. So 2 electrons are bringing the atoms together and 2 electrons are throwing the molecules. So 2 in, 2 out, net is 0. Bonding 2, anti-bonding 2, 2 minus 2 by 2, 0. So what does it mean? He2 doesn't exist even theoretically. Theoretically means even under special conditions. So when I ask you whether H2 plus exists or not, does H2 plus exist? This is my question. Does H2 plus exist? Your immediate answer will be, no sir, H2 plus doesn't exist. Hydrogen exists as H2 only. So you are right in saying H2 plus doesn't exist. But the thing is, what is the intention of my question? Can it exist at least theoretically, H2 plus, under some special conditions? Now then you have to think, okay, 2 hydrogens have lost 1 electron, but still they can manage. How? That single electron will be shared. But that is not, they are not happy doing that, but nevertheless, when they have no choice, that they get. So when I ask, does H2 plus exist, my meaning is under any circumstances, even theoretical circumstances. What about He2? When you say He2 doesn't exist, means even in a dream they can't exist. He2, even under special conditions also, whatever be the conditions, no 2 helium atoms can never be together. They can never form a molecule, He2. Why? The reason is, they have 2 bonding electrons, 2 anti-bonding electrons, He2. Suppose 5 electrons are there. You can create an example suitably. 5 electrons, 2, 2, 1, 6, 2, 2, 2. 6 electrons, 2, 2, 2. When can you have 6 Li2? Li2. 2 lithium atoms, will they exist? Lithium exists as a diatomic molecule. According to molecular orbital theory, Li2 exists. How? 2, these 2 are bonding, these 2 are anti-bonding. 4 minus 2 by 2, 6 electrons. How do you write 6? Li2, total 6 electrons. Sigma 1s2, sigma star 1s2, sigma 2s2. So 4 bonding, 2 anti-bonding, 4 minus 2 by 2, 4 minus 2 by 2, 1. So Li2 exists means, so Li has 1 unpaired electron and another Li has 1 unpaired electron. Assuming 2 lithium atoms meet in gaseous state, they definitely form a diatomic molecule Li2. By chance, there are only 2 lithium atoms, nothing else in this world, only 2 lithium atoms are there. If lithium has a chlorine or lithium meets another one, that's a different matter. If a lithium atom happens to meet another lithium atom, there is no option before them but to form a diatomic molecule Li2. So, Li2 doesn't exist under room temperature, under normal circumstances, or in a solid lithium. Solid lithium, many lithium atoms come together and form a metallic bond among them, but in a vapor state Li2 is theoretically possible. Li2. Next, 7, 2 plus 2, so 2, 2, 2, 1. 8, how do you distribute 8 electrons? 2, 2, 2, 2. 9, 2, 2, 2, 2, 1. 10, 2, 2, 2, 2, 1, 1. Means 2, 2, 2, 2, 1 here, pi 2. So, B2, what will be the electronic configuration of B2? Molecular orbital configuration of B2. So, this is K, K star, this is L, L star. When I say K, K star, it goes without saying that this is kth orbit, this is K star orbit, KLM, KLM, K, this is sigma 2s2. So, this can be ignored. Since these are sigma 1s2, sigma star 1s2, up to 8, bonding and anti-bonding are equal. Sigma 2s2, sigma star 2s2, and pi 2py1, pi 2pz1, pi 2py1, pi 2pz1. So, how many unpaired electrons are there? B2, pi 2py1, pi 2pz1. Therefore, the bond order is how many? 2 plus 2 plus 2. 6 minus 4 by 2. The bond order of B2 is 1, and in that you have 2 unpaired electrons. So, since B2 has 2 unpaired electrons in its molecular orbital configuration, it is said to be paramagnetic. So, B2 exists according to molecular orbital theory. B2 exists, and when B2 indeed exists, it has 2 unpaired electrons in its molecular orbital configuration, pi 2px1, pi 2py1. Now, so that is for 10. 11, it will be 2, 2, 2, 2, 2, 1. 12, up to this, 13, 14. So, since this is the electronic configuration of nitrogen, and beyond nitrogen up to 8 electrons, it is the same, sigma, sigma, everything. After 8, beyond 14, beyond a total of 14 electrons, beyond a total of 14 electrons, this is the configuration. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2px, sigma 2px, pi 2py, pi 2py is equal to pi 2px, pi 2py is equal to pi 2pz, pi 2py is equal to pi 2pz. Then pi star 2py, pi star 2py is equal to pi star 2px, pi star 2py is equal to pi star 2pz, sigma star 2px, sigma star 2px. Look here. So, this is the electronic configuration of 16. Here bonding, anti-bonding, bonding, anti-bonding until now equal. Here you have 2, 2, 2, 6 electrons, 6 are bonding electrons. Next 6 happen to be anti-bond. We have written a total of how many? If you look at it, 8 plus 6, 14 plus 6, 20. In 20, just remember, in 20, last 6 are anti-bonding. In 20, last 6 are anti-bonding. So it's very, very, very easy if you remember well. 14, up to 14, the bond order is 3. 14 electrons, N2. Wherever you have 14 electrons, total of 14 electrons, bond order is 3. What does that mean? Here you have bonding, anti-bonding equal, so you just forget them. There is no rule with this K star, L star. And next 6 are, means 9th to 14th are bonding, 15th to 20th are anti-bonding. Means from 9 onwards, the number of bonding electrons goes on increasing. 9, if the bond order is half, 9 onwards, the 9 to 14, you start with 1 and increase the bond order by half. It's very simple. 9 to 14, you start with 1 and go on adding half. Until you get 3. So 9 electrons, half, 10, 1, 11, 1.5, 12, 2, 13, 2.5, 14, 3. So for every 1 electron, increase the bond order by half. From 9 to 14, starting with 1, increase the bond order by half. Until you get 3. And after 14, for every additional electron, decrease the bond order by half. We'll just of course write from 9 to 20, we will write, that's no big deal. But you just observe, first 8 electrons, among 8 electrons, bonding and anti-bonding are equal. So they are not going to contribute anything for bond order. If you observe first 8 electrons, starting 9 to 20, 9th electron is bonding, 10th is bonding, 11th is bonding, 12th is bonding, 13th bonding, 14th is bonding. So all are bonding electrons. 9th electron, 10th electron, 11th. So anti-bonding means, remember, star only. You don't see any star here, all are bonded electrons. And once again, it is all these have star, all are anti-bonding. So after 9, you have 6 bonding electrons, the next 6 are anti-bonding electrons. Make a conclusion. Up to 9, you can easily write, whenever you need up to 9, you can write, because it's not very difficult. Up to 8, 2, next to 2, 2, 2. 2 bonding, 2 anti-bonding, 2 bonding, 2 anti-bonding. Up to 8, since it is only 4 orbitals, you can write one as one and required. But if you are asked about 13, what you should do is, 14 you know, half less than that, 2.5.